Hi, welcome back. We're up to lecture 16, and the topic of this lecture is analysis of variance. This will be our first lecture on analysis of variance, or for short, ANOVA, of many. Because as you'll see, there are many forms of ANOVA, and it's a very common procedure in basic statistics. So I've divided this lecture into two segments. In the first segment, I'll give you an overview of a one-way analysis of variance, and then in the second segment, we'll talk about post hoc tests and the different procedures that are available to you in order to conduct post hoc tests. So first, let's just go through an overview of analysis of variance. As I said, this is one of the most popular, most common statistical procedures that you'll encounter. And I previewed it when we talked about independent t-tests, and we did multiple pairwise comparisons. And after doing lots of them, I said, well, this is tedious, right? There should be one procedure that allows us to do all of that in one step, and that's ANOVA. So ANOVA is most appropriate when you have multiple predictors. You could have one predictor, you could have multiple predictors that are categorical, and the dependent variable is continuous. And its most common application is for experimental research, but it can be used in non-experimental contexts as well. So if we're conducting experimental research and more than two group means are generated and we want to compare those group means, then we'll engage in ANOVA. If we only generate two group means, then we can just do t-tests, right? If there are two independent samples, then that's an independent t-test. And if there are two means that are from the same people, then we'll do the paired samples t-test or the dependent t-test. Analogously, if you have more than two group means, so three or more, as many as you want, if they're all independent, then we call that a between groups ANOVA. That's analogous to the independent t-test. If you have more than two group means that are all coming from the same subjects, then we call that repeated measures ANOVA. And we'll cover that not in the next lecture, but 2 lectures from now. For now, we're just going to stick with the one-way between groups ANOVA. And for this segment, I'm going to bring back the working memory training example because remember, at the end of the independent t-test lecture, we did a series of independent t-tests, and at the end I said this is tedious and it's problematic because it inflates the probability of a type 1 error. So shouldn't we do this in one giant procedure? And the answer is yes, we'll do it in a one-way between groups ANOVA. So let's assume that we have 4 independent groups of subjects who train for different amounts of time, so 8 sessions, 12 sessions, 17 sessions, or 19 sessions. And then we measure their change in IQ. So remember, everybody took an IQ test before training and after training, and we look at the change score. In all of this, it was a gain, so I'm just going to call it IQ gain. So the independent variable is just number of training sessions. Dependent variable is IQ gain. And the null hypothesis in ANOVA is just that all the groups are equal. Remember, null hypothesis is always that nothing is happening, no effects. So all the groups are equal in IQ gain. Of course, we saw that wasn't the case, right? So we looked at these results before. These are the same results that we generated. Again, these are fake. They look a lot like the data from the experiment I mentioned, but we generated them ourselves. And you see there's a little bit of an increase. When we did the t-tests, this comparison right here was not significant, nor was this one, but all the others were significant. What an ANOVA will do is it's going to tell us, first of all, is there an effect just overall? Is there an effect of training condition? So across these 4 groups, is there a significant difference somewhere? That's what the F ratio will tell us. Then we'll engage in the post hoc tests to figure out exactly where there are significant differences. So as I alluded to, ANOVA typically involves NHST. It doesn't have to. You can calculate these statistics and not engage in NHST, but it's most common that people do. And the test statistic here is not a t-test, but an f-test or f-ratio. A lot of people refer to it as an f-ratio because you can think of it as the variance between the groups or across the groups. And that's good variance. So that's variance that we created with our independent variable, with our treatment, relative to variance within the groups. So students who are in the same exact training condition, who had the same exact number of training sessions, why are they performing differently? So why is one subject or one student gaining more than another in IQ? I don't know. That variance within groups is unsystematic. It's just what I would expect due to chance. So see, this F ratio is an NHST just like all the other ones that we've looked at, specifically t-tests, right? It's what you observe in the numerator relative to what you would expect just due to chance in the denominator. And if you get, say, 2 or 3 times more of an effect than you would expect due to chance, then you're probably going to have a significant effect with p less than 0.05. But let's see. So before we go into that, we need to look at these F distributions. So remember when we did t-tests, we calculated a t-value for either independent or dependent, and then we looked into a sampling distribution from the family of t-distributions to find the appropriate or the corresponding t-value. Same exact thing occurs here with the f-test. We have an f-test and a family of f distributions. The family of f distributions depends not only on how many subjects or how many students are in this experiment, but also the number of groups. Right? In this example, we have 4 groups. We could have 10 groups. ANOVA can handle as many groups as you like. So there are different sampling distributions, and here's what they look like. You can generate that in R. I actually just borrowed some code off the internet to generate those sampling distributions in R. Each different curve varies depending on number of groups and number of people in a group. So let's just take, on average, it's something like that. The most important thing to notice here is it's not like the T or Z distribution, right? The T or Z distribution gave us that nice normal curve, bell-shaped curve. It's not symmetrical because negative values are impossible. It's a ratio of variances. So you see it's bounded at 0. So we can't get negative values. So the expected value under the null hypothesis is just 1. So there's about the middle. Of course, if we get a really large F value, then we'll be way out here. The probability of landing out there, given the assumption of the null hypothesis, is pretty low. It's the area under the curve. So same concept as T and Z distributions, just looks a little different. So back to this concept of an F ratio or F test. I described it as sort of the between groups variance relative to the within groups variance. And I like to think of that as systematic variance relative to unsystematic. Some people like to say it's the good variance relative to the bad variance. In any intro stats textbook, you might see this notation, just mean squares between over mean squares within. Remember, mean squares is variance. I'm going to use this notation down here at the bottom because you'll see as we go into factorial ANOVA, repeated measures ANOVA, this notation will be more useful and generative as we look at more complex designs. So let's take that F ratio, mean squares sub A, where A is the independent variable, it's the manipulation. So in this example, it's number of training sessions. And mean squares S within A is the way to read that error term. So it's subjects within groups. It's the within groups variance. That's the F ratio. Remember, a mean squares is just variance, so it's always sums of squares divided by degrees of freedom. And the number of terms that go into a mean squares is equal to, for A, the number of groups. So mean squares of A, there's just, in this example, we have 4 groups. We're going to compare each group mean to the grand mean to get the variance across groups. And then within groups, we'll look at each individual within a group and see how much they differ from their group mean and calculate variance within groups that way. So degrees of freedom is always the number of terms that go into that variance formula minus 1. So df sub A is just 4 minus 1. df S within A is number of subjects in a group minus 1 times the number of groups. The sums of squares are the more difficult calculation, and because it would take a very long time, this segment's going to take a long time anyway, because it would take a long time, I'm not going to go through and do a calculation by hand, but an example of a hand calculation will be available on the course website for this and for factorial ANOVA, just because it's helpful to walk through the calculations, but not so helpful on camera when the segment's going to run a little long anyway. So to get the between groups sums of squares, again, we just get each group mean and compare it to the grand mean. Just like we calculated variance way back in summary statistics, we're just going to get a deviation score, square it, and sum it. That's the sum of squares. We're going to pre-multiply by the number of subjects in each group, because if they're very large groups, then we have to take that into account, right? But that's it. It's still just calculating variance the same way we did back when we did summary statistics. Variance within the groups, we'll take an individual person in an individual group, their score minus their group's mean. How much are they deviating from the group mean, and why are they? We don't know. That's unsystematic. We'll get their deviation score, square it, sum it, that's sums of squares. Do that for every group, and we'll have sums of squares within, or S within A. Again, degrees of freedom is the number of values that go into that variance term minus 1. So number of levels of the independent variable minus 1. So in our working memory training example, that's just 4 minus 1, or 3. DFS within A, number of subjects in a group minus 1, times the number of groups. And that will add up to the total. The nice thing about analysis of variance, and this is true for factorial ANOVA, repeated measures ANOVA, mixed factorial ANOVAs, is these sums of squares values, these degrees of freedom values, they all add up. So it's mathematically very simple. So compared to multiple regression and things like moderation, this is a breeze. So as I said, if you've made it through multiple regression and moderation analyses, you'll find this, I hope, rather easy, relatively speaking. So all I did was just summarize all those formulas in a table, and it's common to see a summary table, sometimes even printed in a research report, but you'll definitely see this in the output of R, which you'll see as we go through an example. Note that the sums of squares for A and S within A add up to the total, as do the degrees of freedom, but that's not the case for mean squares. So I just X'd those out. We don't need to put any values in here, and of course we're just getting one F ratio because there's just one independent variable. We want to know, is there a significant effect of training condition? Remember, that's an NHST, so it's biased by sample size. If I go back to the summary table, notice that this F statistic has mean square S within A in the denominator. Mean square S within A has degrees of freedom S within A in its denominator. Well, there's the value for that. Notice N. So if N goes way up, then the error term is going to go way down. F will go up, p-value will go down, just like in t-tests. So it's an NHST, it's biased by sample size. So we should supplement it with an estimate of effect size. So the way to do that in ANOVA is through eta squared. This is analogous to R squared in multiple regression. It's just the percentage of variance in the outcome measure, which now I'm calling the dependent variable because I'm assuming experimental research now. It's the proportion of variance in the dependent variable explained by the independent variable. And we calculate it by using sums of squares. So it's just sums of squares for A over sums of squares total. Finally, the assumptions of this analysis are very simple, just like an independent t-test. So we have a continuous dependent variable, probably an interval or ratio variable. We assume it's relatively normally distributed, and then remember that final assumption, homogeneity of variance, which we can test with Levene's test. If Levene's is significant, then we're just going to conduct pairwise comparisons with a restricted error term. What do I mean by restricted? Well, remember in the independent t-test, we pooled the standard deviations from two groups. Here we're pooling the standard deviations or the within groups variance from 4 groups in this example, or as many groups as we want. If we don't have homogeneity of variance, then that pooled term isn't valid. So we should use a more restricted error term. So now let's get back to the example. I'm just going to show you the output that I ran through R. As I said, going through the hand calculations would make this segment even longer than it is. But we'll put some calculations up on the website for you. So we have one IV, one DV. You've seen these data before. There they are. And here's the output from R when we run an ANOVA. So we'll do this in lab, but the function is AOV, and that's right here. You put an AOV, open parentheses, the dependent variable, that's IQ, tilde, then the independent variable. And I just called that condition for the 4 different conditions. If I do the summary function of that ANOVA, it gives me a summary table. So if you see here, this looks exactly like that summary table I showed you where we had sums of squares, degrees of freedom, mean squares, F, and here we get a p-value associated with that F. So let's work backwards. Here's the F value, 10.49. So we have 10 times as much systematic variance or between groups variance as within. So this is a big effect. Okay, and we made up the data so that it would work out this way. So if you look at the p-value, it's very, very, very low. So the area under the curve in that sampling distribution is tiny. It's way out in the end. So where did that F value of 10.49 come from? Well, it's just the ratio of these two mean squares. So 65.36 over 6.23. And where do those mean squares come from? Well, remember, mean squares is always just sums of squares divided by degrees of freedom. So if you want to do the calculations, just do sums of squares divided by degrees of freedom. That will give you the mean squares. And it's always good practice to check your degrees of freedom in your output to make sure they make sense. I didn't mention there were 20 subjects in each of the 4 conditions for a total of 80 subjects in the entire experiment. That means the total degrees of freedom should be 79. Well, if I add up 3 and 76, that's 79. There were 4 conditions, so 3 for the condition degrees of freedom makes sense. And remember, for the residuals or error, it's number of subjects in a group minus 1 times the number of groups. So it's 19 times 4 or 76. So that's the summary table. That's the F ratio. It's significant. So we have a significant effect. But the F ratio and just that part of the ANOVA doesn't tell us which pairwise comparisons are significant. So do we now have to go back and do the independent t-tests again? Well, no. There are built-in procedures for that, and those are called post hoc tests. So that's the next thing you see in the output is I used a procedure called Tukey here, and in the next segment we'll get into the nitty-gritty about different post hoc tests, but what that does is it allows me to compare all the different groups. So let me go to the full output now, and you'll see at the top the summary table we just looked at, And now you'll see the output of this Tukey procedure, which does all the pairwise comparisons for us. But remember, what's important to remember now is you can't just do lots and lots of pairwise comparisons like we did when we did independent t-tests. You'll inflate the probability of a type 1 error. So what Tukey's procedure does is it does all the pairwise comparisons but adjusts the p-values as to not inflate the probability of type 1 error. And you see that in this last column, which is called p-adjust. It's adjusted the p-value accordingly. So just to demonstrate that, look at the p-value for the first row in the Tukey output. That compares the 17-day condition to the 12-day condition. And the p-value is 0.0326 something. If we go all the way back to the independent t-test lecture, do that exact pairwise comparison, but as an independent t-test, no correction, then we get a p-value of 0.0067. So much lower, right? Because we didn't correct for multiple comparisons, which was wrong. So the Tukey procedure is built in as a supplement to ANOVA. So to wrap up this segment, ANOVA is used to compare means, group means, typically in experimental research. We're going to assume a categorical IV and a continuous DV. We have to check into that homogeneity of variance assumption because we're pooling variances across different groups. And we do that with Levene's test. And finally, we need to look for where the pairwise comparisons are significant by conducting post hoc tests such as Tukey's procedure. And there are actually multiple procedures at your fingertips in R. So I'm going to do a whole nother segment, the next segment, on post hoc tests that you can use to get at those significant pairwise comparisons.